We're surrounded by these LLMs now, these large language models, and you see them doing these really amazing things with language writing, summarizing, even coding. But have you ever stopped to think about what they fundamentally can't do?
Hmm.
They reason with language, sure, but ask them to calculate something or fetch some live data from the web, and they hit a wall.
You've hit the nail on the head. That's exactly the puzzle we're digging into today. These LLMs, they're masters of language, but they don't inherently have a way to interact with the real world, to crunch numbers directly. Like they can explain how to do a calculation, but actually performing it, they need help from outside.
Yeah, absolutely. And that's what brings us to this really exciting frontier tool learning. It's this idea of basically giving these AI, these linguistically gifted but practically limited AI, the ability to actually use tools to expand their capabilities. It's about letting LLMs move beyond just words.
And for you, the listener, you've probably seen these models in action, and maybe you've wondered how they could become even more powerful, how they can actually do things in a more direct way. Well, that's what we're focusing on today. We're not just talking about tool learning broadly. We're going deep into a really innovative approach that's tackling a core challenge. How can these LLMs learn to use a huge and ever-growing set of tools, even ones they've never encountered before?
Exactly. We're doing a deep dive into a new method called chain of tools, co-tools for short. It's a fascinating development coming out of Suzhou University. They're really grappling with some of the most interesting questions in tool learning research, especially this whole issue of unseen tools. So let's get into the specifics, shall we?
Absolutely. A good place to start might be by mapping out the existing landscape. So in tool learning, we've generally seen two main strategies emerge. The first one, kind of the most straightforward one, is fine-tuning. What this means is you train the LLM on data that specifically shows how to use certain tools.
So you're directly baking in the knowledge of how to use certain tools right into the LLM during its training.
Yeah, precisely. You can think of examples like API Bang in Tool LM. The model learns to call specific APIs to understand the patterns of using those tools.
Okay, so for those specific tools it's seen during this fine-tuning process, it becomes pretty proficient at using them, right?
Right. But, from an academic perspective, there are some real drawbacks to this approach. First off, this very focused training can sometimes have a negative impact on the LLM's more general linguistic abilities, like, those amazing emergent abilities that LLMs have, even the ability to reason step by step, which we call chain of thought, they can get diluted. It's a trade-off between specialization and broad competence.
Yeah, that makes sense. Focusing too narrowly on one thing might take away from the other areas. And also, I'm thinking, what if there's this brand new, incredibly useful tool that comes along, one that the model hasn't seen during training? What happens then?
You've landed on the second major limitation of fine-tuning. There are variations like Toolkin GPT, which try to lessen the impact on the core model by only fine-tuning the representations of special tool tokens. But at the end of the day, it still can't really interact with tools that are completely outside of its training vocabulary. It's limited to what it's seen before.
So, fine tuning works well for familiar tools, but it has trouble with novelty, and it could potentially mess with the core LLM's abilities. What about the other strategy that researchers have been working on?
Right? The other main approach is in-context learning, or ICL for short. Methods like Hugging GPT and Agent Bench fall into this category. The idea here is, instead of this extensive retraining, you give the LLM examples of how to use a tool right within the prompt itself. It's like showing someone a new piece of software and giving them a quick demo, saying, look, here's how it works.
Oh, I see. So it's learning to use the tool based on those specific examples provided in that one interaction. That seems a lot more flexible for new tools, right?
Yeah, definitely. It offers a lot more flexibility when it comes to handling tools the LLM has never seen before. But there's a catch, and it's a significant one from an academic standpoint: efficiency. Especially when you're dealing with a large and diverse set of tools, ICL becomes less practical. Imagine having to include detailed demos for dozens or even hundreds of different tools in every single prompt.
Right.
The context window for these LLMs, it's big, but it's not infinite. These prompts can get really long and complicated, which can impact both performance and how much computing power you need.
So we have these two main methods, and each one has its own issues. Fine tuning is good for the tools it knows, but not so adaptable and maybe even harmful to the base model, while in context learning is flexible but doesn't really scale well when you have lots of tools. What's the fundamental problem that this Suchar University research is trying to solve then?
Okay, so the core problem, as this new work very astutely points out, is this: How do we give LLMs the power to effectively and efficiently use a massive and constantly changing set of tools, including those they've never encountered before, without sacrificing their core reasoning abilities? That's the real challenge, and that's where Chain of Tools, or CoT, comes in with a fresh approach.
Okay, so CoTools aims to solve this big challenge. What makes their approach so innovative, so different from what's come before?
The key innovation lies in how they approach fine-tuning. Unlike those traditional methods that actually change the core LLM's weights, CoTools is specifically built to work with what we call frozen LLMs.
Frozen LLMs.
Yeah, this means the underlying network of parameters that gives the LLM its general language understanding, it stays untouched during the entire CoTools training process. This is a big departure from the norm, and it's crucial for preserving those all-important general abilities that often take a hit with conventional fine-tuning.
So instead of fundamentally retraining the whole LLM, they're adding on these specialized modules or pathways, if you will, that are specifically for tool usage.
Exactly. The heart of CoTools lies in this clever way. It uses the LLM's existing linguistic understanding, the semantic information already encoded in its hidden states, to make smart decisions about when and which tool to use during its reasoning process, which, as we've mentioned, is called chain of thought, CoT. This deep connection with CoT is a big part of what makes CoTools so novel.
So it's taking advantage of the LLM's natural language skills to guide its use of tools. How does that actually work on a technical level? What are the main parts of CoTools?
CoTools has three key components that work together: the tool judge, the tool retriever, and the tool calling mechanism. Let's start with the tool judge. Its job is to figure out, at each step as the LLM is generating its response, whether it would be helpful to call an external tool at that moment. And it makes this decision based on the hidden state of the current token being processed. This dynamic step-by-step decision-making is a big step forward compared to those approaches that might only decide about tool usage at the very beginning of a task.
So as the LLM is going through its chain of thought reasoning, the tool judge is constantly checking if calling in an external tool would be useful at that specific point in the thought process.
Exactly. Think of it like an internal expert system that knows when to reach out for external knowledge or abilities. Now, if the tool judge decides that a tool is needed, the tool retriever steps in. Its role is to choose the most appropriate tool from a potentially massive collection of available tools. And this is where CoTools shows a really novel way of dealing with unseen tools.
How does it handle that, effectively sifting through a potentially huge number of tools, especially those it hasn't seen in its training?
The tool retriever uses this concept called semantic similarity. It creates what's called a query vector, which represents the LLM's current reasoning context. At the same time, it has access to these tool vectors. Now, for tools it's seen during CoTools training, these vectors might be learned or representations. But here's the key for unseen tools. These tool vectors can also be dynamically created from the text descriptions of the tools themselves. So even if the LLM has never encountered a specific tool before, it can understand what that tool is supposed to do based on its description and match it to the current need using semantic similarity. Basically, it finds the tool that speaks the same language as its current line of reasoning.
That's a pretty elegant solution to this unseen tool problem. It's not about recognizing a tool it's seen before. It's about understanding the function of a tool from its description.
Precisely. It's all about functional understanding and retrieval. Once the tool retriever picks out the best tool, the final part, tool calling, kicks in. And interestingly, for this stage, CoTools actually leverages in-context learning. It gives the frozen LLM a few examples of how to interact with a chosen tool, giving it the context it needs to generate the right parameters to call that tool. And then, after the LLM generates these parameters, the tool is executed within their experimental setup, of course. And the result is fed back into the LLM so it can continue its reasoning process.
Okay, so to recap the innovation here, CoTools uses the frozen LLM's existing understanding of language to dynamically figure out when to use a tool, that's the tool judge. Then it intelligently identifies which tool to use, even for novel tools, by understanding their descriptions, that's the tool retriever. And finally, it uses in-context learning to guide the LLM in actually executing the chosen tool that's tool calling. It's a really interesting combination of techniques.
Absolutely. And to really test this approach, especially how well it handles a large number of unseen tools, the researchers created a brand new benchmark dataset called SimpleToolQuestions, or ST questions.
They made a whole new data set just for this. That sounds like a significant contribution in itself.
Oh, definitely. The existing benchmarks in tool learning, they hadn't really focused heavily on this scenario where you have a ton of unseen tools. STQuestions includes a total of 1,836 tools, and get this, a large chunk of them, 837 to be exact, are completely unseen during the testing phase. This allows for a much tougher evaluation of how well a tool learning method can generalize to new tools just based on their descriptions.
So it's not about just recognizing tools it's seen before. It's about a more abstract understanding of what different types of tools do and how to use them based on information about them.
Exactly. This data set gets us closer to real-world situations where new tools are popping up all the time. So let's see how CoTools perform, shall we?
Let's dive into those results. What did they find out about how well CoTools works?
They tested CoTools on a bunch of different types of reasoning tasks. First, they looked at numerical reasoning using datasets like GSM8K-XL and FuncQA. They found that CoTools was either on par with or even better than existing models like zero-shot ChatGPT and TokenGPT. Interestingly, they also noticed that CoTools often performed even better when it was combined with stronger base LLMs like Mistral 7B. This really highlights the importance of the base LLM's reasoning abilities in all of this.
Yeah, that makes sense. If the base LLM is better at reasoning in the first place, it's probably going to be better at using tools too. What about tasks that involve finding and using knowledge?
For that, they use datasets like KAMEL and, of course, their new STQuestions dataset for knowledge-based question answering, KBQA for short. And here, CoTools really shined, especially when working with synthetic training data and, most importantly, when dealing with a large number of tools, both seen and unseen. It outperformed TokenGPT quite significantly.
What about those all-important unseen tools in the ST questions dataset? What were the results there?
This is where CoTools showed its true innovation. It actually managed to achieve non-zero accuracy when it came to selecting and using unseen tools on STQuestions, a big improvement over TokenGPT, which had zero accuracy for unseen tools. The researchers attribute this success to CoTools' clever way of using the text descriptions of these unseen tools for retrieval. It's really about understanding what the tools do, not just memorizing the ones it's seen before.
That really validates the whole idea of using tool descriptions to generalize to new tools.
Right. They also observed that CoTools was pretty robust, meaning it still performed well even when it was trained on synthetic data of lower quality. They think this might be because of the contrastive learning approach they use to train the tool retriever. This tells us that it can learn to differentiate between tools effectively even when the training data isn't perfect.
That's a good sign for real-world applications where you might not always have perfectly clean and organized training data. Now, the outline mentioned something about an analysis of hidden states. That sounds like they went even deeper with their investigation.
Yeah, that was a really insightful part of their work. They dug into the LLM's hidden states, those internal representations that the model forms as it's processing information. And they made a really interesting discovery. They found evidence that specific dimensions within these hidden states are actually more important for the task of tool selection.
How did they figure that out?
They did some really clever experiments where they specifically tweaked the learning rate for a certain weight matrix called Wethermake that's connected to the tool retriever. By looking at how these adjustments affected the model's performance in choosing tools, they were able to work out which dimensions were the most influential.
So they were pinpointing the specific neural pathways, if you will, within the LLM that are the most active and important when it's deciding to use a tool.
Precisely. And what was particularly striking is that by focusing the learning on just a subset of these key dimensions, CoTools could still perform almost as well as it did originally. This suggests that there's some level of specialization or modularity in how information relevant to tool selection is encoded within the LLM's internal representations. It gives us a really valuable clue for understanding how these complex models work.
Wow, that's really pushing the boundaries of understanding what goes on inside these LLMs.
It is, but in the spirit of good science, the researchers were also very upfront about the limitations of their work and suggested some directions for future research.
Yeah, it's always important to keep that critical perspective. What limitations did they point out?
They acknowledge that LLM tool learning is a very young field, and many of the data sets that are available, while they're useful benchmarks, they might not fully capture all the complexities of how tools are actually used in the real world. They also mentioned that their experiments didn't really explore tools that produce multiple outputs, where a tool gives you back several pieces of information, and the LLM has to figure out which ones are relevant. And finally, they pointed out that there isn't a really large-scale, real-world tool set with nicely structured data that would allow for a truly comprehensive evaluation of the whole tool learning pipeline under realistic conditions.
Those are all important points to consider as this field keeps developing. What did they suggest for future research directions?
They emphasized the need to better integrate LLMs with tool learning to tackle more complex real-world applications going beyond these current benchmark tasks. And of course, they plan to address those limitations we just discussed, like coming up with better ways to handle tools with multiple outputs and working towards creating more comprehensive and realistic datasets for tool learning.
It sounds like the focus is really on taking these exciting academic advancements and turning them into something that's useful in the real world.
Exactly. CoTools is a big step in that direction.
So for you, the learner, I hope this deep dive has given you a good grasp of this really cutting-edge area of AI research. CoTools seems to be a truly innovative way to help LLMs interact with a vast and ever-changing world of tools, even ones they've never seen before.
The key innovation is in how it takes advantage of the LLM's pre-existing understanding of language as the basis for tool learning. The new architecture, especially the tool judge and tool retreater, and that focus on enabling generalization to unseen tools through their descriptions, are really important contributions.
And from an academic perspective, this work gives us not just a novel method in CoTools itself, but also a new benchmark dataset in ST-Questions, which really raises the bar for evaluating tool learning methods and their early investigations into the interpretability of those hidden states. That gives us a really fascinating peek into how these models work when they're choosing tools.
It certainly does. This research is not only technically innovative, it also helps us better evaluate tool learning methods and understand how LLMs represent and use external knowledge and capabilities.
As we wrap up here, I want to leave you with a thought. Think about the implications of AI agents that can learn to use new tools on the fly as they appear. How could this change the way we interact with technology and solve problems in the future?
It points to a future where AI agents become incredibly adaptable, able to take on a constantly expanding range of tasks. If you're intrigued and want to explore further, I highly recommend checking out the original Chain of Tools research paper by Mengsong Wu and her colleagues at Soochow University. And, dive into the broader field of tool learning. The linked GitHub repository has the code and data for this work, which could be a good starting point.
Absolutely. This is a rapidly evolving field, and CoTools is a really insightful and innovative contribution. Thanks for joining us on this deep dive. We hope you found it informative and thought-provoking.